Okay, good morning, class. You're on to MAMU with Jarvis, and it's a time to have mathematics. And this is grade 10 mathematics. Today, we'll be considering algebra, and we'll continue from where we stopped, which has to do with indices. We've covered a number of laws in indices, and taking us to the next level, we'll quickly have a rundown of the laws we have considered. I always make it a point of duty to tell my students that it's not so important to know the order of the laws. What's most important is for you to know that these laws exist and learn how to apply them. The application of the laws becomes more important than just knowing the laws. So we'll go over the 4 laws we have looked at so far, and then in no particular order, and then we'll use that as a basis to build on from where we had stopped. So let's look at that quickly. Now, laws of indices. There is one, let's say number 1, that says a to the power of x times a to the power of y will be equal to what? A to the power of x plus y. The concept of indices is a concept of how many times a base is being multiplied. The concept of indices is a concept of how many times a base is being multiplied. Let's imagine I have something like this, 2 index 4 or 2 to the power of 4. This gives us the idea of 2 being multiplied 4 times. So this 4 represents how many times this 2 is being multiplied. So this becomes the index, and this becomes the base, or the reference base, as you may choose to call it. So this is what we're talking about. Now, what now happens when we have a setup like this? For those of us who have witnessed my previous classes, you would agree with me that I had said the laws of indices work best when you're considering the same base. It has to do with the same base. So when the bases are the same, what happens? That's when the laws will work. You get that? All right, so for this, you're going to have a to the power of x plus a to the power of what? Y. So when the bases are the same and you're multiplying the numbers, this is a number, this is another number. This number has a base and an index. This number has a base and what? Another index. So when you multiply them, what happens? You are essentially adding their index. You're essentially adding their indices. So that's what's happening here. We'll take practical examples, or I may refer you to some problems I've solved earlier. Maybe towards the end of the class, we'll look at that. We're just trying to have a review of what we've done so far. Now, number 2, if I have a to the power of x divided by a to the power of y, this essentially will mean a to the power of x divided by a to the power of y. And this essentially would mean that I am subtracting their indices. I'm doing what? Subtracting their indices. That's the beautiful thing about this aspect of math. You're essentially subtracting their indices. So when you divide numbers of the same base, what you have done is that you have subtracted their, or you have done subtraction on their indices. All right, that's the second one we treated. The third one we treated was concept of a raised to the power of 0 equal to 1. I did a very thorough job here. It's called the concept of zero index. I don't know if I posted that video, but I think I'll do well to post that video so that you're able to understand how this is proven. You can actually prove this. It's possible. So you look up that video and you'll be able to get a thorough understanding of how this is done. The next one is the one I call the law of reciprocal. The law of what? Reciprocal. Some books we call it the law of negative index. If I have a to the power of negative 1, this will give me 1 over a. This essentially is a reciprocal, a concept of reciprocal. When you say the reciprocal of a number, what do you mean? The reciprocal of a number, what do you mean? It means find that number by saying 1 over. That's what it will mean. So if I say find the reciprocal of 2, the answer will be what? 2 raised to the power of minus 1, which will be what? 1 over 2. So the reciprocal of 2 will be this, 2 raised to the power of negative 1, and there will essentially be what? Half. So there's so much more to come there. And this is just one case scenario on this. So this is where I will start off my work from. I'm going to start off my work seriously from here. All right, so let me give you some time to take care of this. Okay, so let's get back to work. Now for case 1, I'm taking a case where I just have a to the power of negative 1. And I've established that that will be what? 1 over a. Now, there's also an expanded form of this law. Maybe we should call this case I1, and let's call this case I2. There's an expanded form of this law. What's the expanded form? We have a over b all raised to the power of negative 1. Now, what a reciprocal concept we do here is to toggle, to turn. That's what it does, to toggle. It will turn it. So what the effect you see now is that the denominator becomes the numerator and the numerator becomes the denominator. So if you have this, the interpretation is a over b, the reciprocal of what? A over b. What you're going to get will be b over a as your final answer. B over a as your final answer. So this is case 1. This is case 2. Some books will not show this to you. It's not because they do not know, but because I've taught this for years, and I discovered that it's better you have a large knowledge or a broad knowledge of these concepts early, so that when you start to see them again in problems, you can identify them and know what to do. So this is how you're going to handle this particular case. So let's go to number 5. Number 5 is more like an extension on number 4. So in number 5, we call it the law of negative index. Now, let me also shock you that the law of reciprocal is also under law of negative index. But in the case of reciprocal, we are considering that the index is what? 1, is negative 1. Now, when the index is on negative 1, what do you do? Take note of this also. When we consider negative index at this level, we're looking at a whole number, because we're going to come into something else that will expand on that idea. But the idea here is that the law of negative index applies to a negative whole number. So essentially, what is a negative whole number? By way of addition, a negative whole number, I'm going to put a little note here just to build up, to connect. Now, this is where, I always like to talk about the Marvel's Cinematic Universe, because those guys are doing a very awesome job in trying to connect our intellect. Now, I'm now trying to connect an idea from arithmetic now to algebra. Look at this. A negative whole number is a part of integers. So we can say that a negative whole number is an integer. So I'm connecting previous knowledge now to an idea I want to front. So if you look at this, it means that this is an added note for you, to understand the concept very well. Now, from this, you discover that what does the law now talk about? If I have a to the power of negative n, where n is a whole number, is what? Where n is a whole number. So n, where n is a whole number. So What will this be? This will be equal to 1 over a raised to the power of n. Because I've already told you that a raised to the power of minus 1, a raised to the power of minus n is actually raised to the power of minus 1 is actually 1 over a. Now let me expand on this idea. This will mean a to the power of negative 1 times n. I'm expanding on this idea because this one will mean negative 1 times n. So it means that negative n is equal to negative 1 times n. I see what I'm trying to do. I'm bringing some things you've learned before. So ideas you've gathered before. You start to see the relevance of those ideas. And these are the ideas that will determine whether you understand what we're doing now or not. So you discover we may need to be going back to previous knowledge, draw from previous knowledge to help further what we need to study. So this is what you have. This will now be equal to what? Watch this. This will now be a 1 over a all, because this is 1 over a, all raised to the power of n. Don't ask me, uncle, what are you talking about? You will see this explanation much later. Okay, now remember that anything raised to the power of 1 is what? 1, is that not? Good. But I'll just leave this at so let me leave it at this. When I come to a new rule, so this answer is the same as this. So 1 over a all raised to the power of n is also equal to 1 over a raised to the power of n. Some people will be asking lots of questions. Uncle, I don't understand what this is. Don't worry. It's done intentionally. When we come to look at other principles, you will understand why this thing we have written here is what? Correct. All right. All right, so in law 6, we have a setup that says, what about if I have a number to a particular base and then everything is raised to another base? Wow, this may not be very easy for us to perceive at first, but I'll start with an example to help you get where we are heading to. If I say 2 to the power of 3 all raised to the power of 4, what does this mean? From your knowledge of ordinary math, this would have meant 2 raised to the power of 3 4 times. 2 raised to the power of 3 4 times. So you'd have had this. Everything here raised to the power of, if I had said 2 raised to the power of 3 would have made 8 raised to the power of 4, is that not? But now, this one means everything in this bracket multiplied 4 times. Now, if you look at this, how many of these 3 can you see? It's 4. So it would mean that when I have a setup like this, it will mean multiply this one 4 times. Now, let's see whether what we have here will correspond with what you have here. We had said before that if you multiply bases, what you are doing is that you are adding their indices, provided the bases are the same. So this will be 3 plus 3, 9, plus 3, 6, sorry, plus 3, 9, plus 3, 12. What is 3 times 4? That will be what? 12. So it follows that anytime I have this setup, I'm actually saying do this, which invariably will what? A raised to the power of what? X, Y. Are you seeing that? That's what that will mean. A raised to the power of what? X, Y. So every time you see this kind of setup, an index in an index, it would mean that you should multiply their bases. Sorry, multiply their indices. So that's the setup for theorem 6. So in 7, we have what is called the law of fractional index, or sometimes they say the law of fractional indices. All right.
So law 6 was what?
Okay, so we go to law 7. Law 7. Law 7 talks about what? Fractional index. It will mean that the index we are talking about is now a fraction. Notice that when we started this law, or we started looking at the laws of indices, the index or the indices we've been considering have all been whole numbers. I know that you've observed. Now, what happens when the index in question is a fraction? How do you handle that? That's what this law is trying to take care of. So if I have a to the power of x over y, a to the power of x over y, how do you handle this? But this is just one case scenario. We actually have another case scenario where we have a to the power of 1 over y. And I think it will be better for me to take on this first before I bring you to this. Sometimes students find it difficult to understand this because they don't have a good grasp of what this is. Now, so we'll go to case 1, where we have a to the power of 1 over y. What is the interpretation of this? This will be equal to the y root of a. The y root of a. Essentially, when the index is a fraction, it implies look for the roots. So let me put that in statement. When an index is a fraction, say 1 over y, for instance, comma, the effect on the base, say a, when an index is a fraction, say 1 over y, the effect on the base, say a, will be to find the white root of a. That's just to sound mathematical, but let's try to get a direct interpretation of that. That's just to sound mathematical. Let's get an interpretation of that. I don't want you to always run away from all these technical mathematical things, because at some point in time, you will have to work with them. So for now, really don't get worked up with these ideas, but I'll try to make it very simple, the implication of what I've written there. Now, what this means is this. Let's take an example. For example, I have 4 to the power of 1 over 2. This will mean these 2 here symbolize square roots. So this will be the square root of what? 4. I seen that. And what's the answer? The answer will be what? 2. Because you already know. I'm coming from what you already know. You already know that the square root of 4 is what? 2. Now let's assume I have 8 and I have 1 over 3. Because these 3 here will represent cube roots. This one here will represent what? Square roots. Are you seeing that now? So this will now be the cube roots of what? 8. And you're already conversant with that the cube root is equal to what? 2. Is that not? You're already very conversant with that. But that's where you are going to start from. And then I will use this setup now to introduce you to where you should be going to. So let's allow ourselves a bit of break. So let's look at the second aspect of this law. Now, remember that I already taught you that this one, a raised to the power of 1 over y, will be equal to the white root of what? A. Is that not? We've already taught you this, so you know this. Now, what happens when you have a to the power of x over y? I hope you know that this will be the same thing as saying a raised to the power of x times 1 over y. Let me do an extension this way. If I have x over y, this means x divided by y, is that not? But this can also mean x times 1 over y. Numerator times denominator. Denominator is always expressed below. You get that? So this is what the setting should look like. Now, this is the idea you need to bring here. So it will be x times what? 1 over y. This will mean a raised to the power of x, or a raised to the power of what? 1 over y. We treat roots before we treat power, or before we treat the numerator. So that will be what? Raised to the power of what? X. Remember that there's a rule we have done before. So you see now that I am bending, I am actually using that rule backwards now. Before we said that, remember we said that a raised to the power of x, y would have given you what? A raised to the power of x into a raised to the power of y would have given you a raised to the power of x, y. Is that not? But now imagine I'm coming from this point and I'm going backwards this way. Now in your mind eye, now remove this, change it to times 1 over y. What would you have? You have what? Times what? 1 over y. You can also have this to mean a raised to the power of, treat this one first before you treat this one. Or let's even make it easier for us to perceive. Let's assume I'm writing a raised to the power of 1 over y times x. I think that's something some of us can easily perceive. This will now be a raised to the power of 1 over y times x. What is a raised to the power of 1 over y? It is the white root of a, everything raised to the power of what? X. So that's how this law applies. So this one will mean find the white root of a, and then after that express to the power of what? X. So that's what this rule is. If you can't catch the rule so well now, don't freak out. We will solve lots of examples. In fact, our next class will focus on solving examples. So in solving those examples, your eyes will open to the rules and see how they are being used. Because the most important thing, like I've told you, is to identify the rule to use and how you are going to use it effectively. All right, so I'll give you some time to copy now. Okay, thank you very much for your time, and I'll trust to see you in my next class where we'll solve just problems involving indices. All right, thank you.